So as we were saying in the last video, we basically established that the gravitational force inside of the planet is directly proportional to the distance from the center, which means that you can actually use this property to analyze what will happen if hypothetically you had a tunnel going through the earth like this, and somebody happened to take a little object at the beginning of this well or tunnel, a little object of mass m, and you just drop it. If you just drop this object, what sort of motion will you happen to observe as the object falls down the well? Well, Newton's second law comes to our rescue here, as well as a little bit of vector analysis. You know very well that if the object is at this distance, then because of the law of universal gravitation, you have this force, and we said that this force in its vector form Fg is equal to minus g m m over the radius of the planet cubed times r, because it is a function of the height. However, it is a negative because you have this always pointing towards the center of the circle. When the object is at this distance, for example, it's pointing towards the center, although it is a smaller force. When it is at this position, it turned around and it's pointing towards the center. And when it is all the way over here, if it happens to go there, then it's gonna be much larger towards the center. So you should be suspecting that something is going to happen here that you've already seen. According to this, the net force exerted on this object is equal to minus g m little m over r cubed. Now, all of that is very scary, but it's only a constant, times r, which is the distance from the center. But also, according to Newton's second law, the net force is equal to the product of the mass of the object times its acceleration. Minus g m m over r cubed r. And so, what we're saying, basically, is that this acceleration doesn't actually depend on the mass of the object. It only depends on the mass of the planet and the radius of the planet. And so, you should be familiar with this by now. The second derivative of the position relative to time plus g m over r cubed times r is equal to 0, which is, as you very well know, a harmonic equation, and that means that this object will show a motion basically called simple harmonic motion. Now, under these circumstances, your angular frequency, your omega, comes from this constant over here, and so omega squared is equal to universal constant times the mass of the planet divided by the cube of the radius. Therefore, omega is the square root of that. And if you remember from your last unit, the period should be equal to 2 pi over omega, which is the same as 2 pi square root of radius of the earth cubed divided by gm. Now, I will ask you to make the calculations for this and show that with a mass of approximately 5.97 times 10 to the 24th kilograms and a radius of approximately 6.38 times 10 to the 6 meters, you will get a period of more or less 85 minutes. Please go home and do yourself some numbers, and let's see if we can prove this, that this object can travel all the way to the other side in just under 3/4 of an hour. And this is of course under certain very drastic assumptions that the density is uniform and that the planet is not spinning. But it is a good approximation of what you could have achieved if you drill, for example, a through and through tunnel in the moon or somewhere like that. So let's go ahead and try the numbers.